a series of vectors and graphs. And I've got them numbered. Okay, so if you read through the lab, like down here on number 1, draw a free body diagram of the block. It's being pulled to the wood surface. Choose a scale such as 2 centimeters equal Newton. So diagram number 1 is going to look like this. So this is the free body diagram showing all of the forces. So diagram number 1 is going to look like this. You're going to draw your block. You don't have to shade it. You don't even have to draw it as a block. You can just put a dot. You can have 4 forces. Fg, force normal, force applied, force friction. Should look like a big plus sign when you get done, okay? But this is to scale with a ruler, okay? These are not just random lines that you're going to draw. These have to be to scale. I want to see what the scale is. Label them. Fg, force normal, all that stuff. That's what diagram number 1 is going to look like. Then, on diagram number 2, you're going to draw these tip to tail. So diagram number 2 is, I always draw my gravitational force first. Here's my force applied, force normal, force friction. Okay? I would recommend that you use the same scale as on the first one. Where should you end up?
Origin.
Back to the origin. Again, these are done on a completely separate sheet of paper. Label them, number 1, number 2. Okay? Then, once you get done with that, then you're going to add the weights to the block, and then you're going to see how much force it takes to pull it. But by measuring the force applied to pull it, what else are you indirectly measuring?
No.
Nope.
The
Rhymes with force friction.
force
Force
friction.
friction.
Force friction. So by measuring how much force it takes to pull it, you're also measuring the force friction. You're measuring how much force you have to give to the gravity mafia, or excuse me, to the frictional mafia. So here's going to be the third thing you're going to do. You're going to draw a line, and you're going to plot force normal on the x-axis, and you're going to put force friction on the y-axis. But you're going, oh, Mr. Burkamp, we don't have force friction. Yes, you do. You have the applied force. By having the applied force, you're going to have the force friction. So you're going to come in here, and it should be pretty linear, okay? Because the more the block weighs, the more friction there is to pull it. So explicitly, I tell you, circle the points on the line of best fit, write the coordinates on the graph, and show me how you calculate that slope. So you're going to have these points. You're going to come in here. You're going to draw a line of best fit. You're going to have a couple of point circle. It might start at 0, 0. It might not. Okay, it just depends upon what the data is. So that's going to be graph number 3. The fourth one over here is, this is the one that's going to come from that force table one. That one, on this one, you're going to take these and you're going to draw this tip to tail. So you're going to have vector A, vector B, vector C. Drawn to scale. Again, choose a scale. Maybe you wanted that 2 centimeters equal Newton. If it's big enough, you might bet 1 centimeter equal Newton. That's making a difference. But tell me what that scale is. You have a protractor. You are going to draw these to this correct orientation. In an ideal world, you're going to end up exactly back at the origin because the system is in equilibrium. Realistically, you're probably not. You might be off by a little bit. Now, if you draw this and you get this, something has gone horribly wrong. Okay? It should be pretty close back to that origin. So, I'm done. Here's what you need to focus on. Get the data. Okay? Get the data. We're going to continue this lab on Monday. Focus on getting the data. Focus on getting the graphs drawn. We'll talk about the theory part of it on Monday. Okay? All right, ready to break.